Thank you very much for this very kind introduction. This is a very strong microphone clamp. I'm a weak physicist. And that's related to what I'm doing my research, because I'm researching, I'm doing my research with nanoparticles, and I want to show you today how to see invisible stuff. And you might wonder, well, invisible stuff, maybe there's a good reason why this invisible stuff is invisible. For example, I believe that the creator, at the 8th day, he thought, well, he felt a bit boring. He rested on the 7th day, and now he felt boring on the 8th day and thought, well, what could I do? I've created the world, everything is there. Let's create something that is new, but that people don't see. So let's create some invisible stuff. And he created invisible nanoparticles. So he put them under the carpet of creation, and then he said, well, yes, and you might still wonder, well, why are they important? Because they're under the carpet of creation. And I say, well, nano is everywhere. Well, there should be nano everywhere. Now is nano everywhere. And I don't know how your summer was. For example, in Bavaria it was a great summer, and in Bavaria we use sun cream to protect ourselves from the sun. In the sun there is titanium dioxide nanoparticles that protect us from the sun. It's actually the same stuff that makes white wall paint white. So if you really want to be sure, take white wall paint. It's not so nice, but you'll never get sunburned. Another example, and that's more for me because I'm a lab rat, you know, I don't go to the sun, I stay in my lab. And maybe at some time I go to churches, medieval churches like St. Peter and Paul's Cathedral here in Brno. You find those great colorful windows here. This window, and especially the red parts in those glasses, already at medieval times people knew that if you put metal salts to those glass melts, you get colored glass. In the red glass there are gold nanoparticles. I like them a lot because I did a lot of research with them. Now it's influenza season. If you get, you can protect yourself by getting vaccinated. There the viruses are dead. If you get ill, then they're alive and you have a problem. But still, viruses are nanoscaled particles. And the very reason you're alive, ladies and gentlemen, that's because nanoscaled proteins, for example, nanoscaled structures, biostructures, construct life, program life. And that's how they, at least as a quantum optician's point of view, they look like. And because nano is everywhere, they're all over the world, all in our everyday life, there is nano. We should investigate them, and those proteins, they can wiggle with their airs, and I think that's a very important reason to investigate them. That's actually what we did. So we took a lot of nanoparticles, and but I brought you, because they are so small, I brought you a model. Look. Already also a third model. So if on a first look, they all are yellow, you see? All yellow. But if you look them, for those in the last row, you see it printed here. And if you look at them in detail, then we see that this has a weird haircut. This is very round, and this has turned feet. Now this is the turned feet guy, and this is the weird haircut. And if we look in detail, we see that they all are different, so we have to investigate them individually. That's what we did. We took a laser. We took a detector. Don't take bachelor students' eyes. You don't have so many bachelor students. We take a nanoparticle, shine in light, and then nothing happens, because also the best laser focus, this screen is not a good example because it's quite big. Imagine the best laser focus is half the screen, yes? And you take the nanoparticle, and you see it doesn't get really darker. So it's not really dark. And so we played a trick. We put mirrors around the nanoparticle, and light circulated for 30,000 times. We took the best mirrors you can get. Light circles 30,000 times around, and after 30,000 reactions, you believe me that a gold nanoparticle, as small as it might be, it takes out enough light that we can measure something. So we wrote the publication, we're happy, and thought, well, Now it's lunchtime. What should we do afterwards? So we had, you believe me that gold nanoparticles are not transparent. But that they take light and are easy to detect, but what happens if the particle... no, that's too far. Now, what happens if the particle gets transparent? So if with gold, with those gold balls, it's already complicated. It's not easier with transparent nanoparticles. And also in large scales, I give you an example. It's not easy. So look at this bird. This bird says, well, today I'm the early bird, and what does an early bird? It gets a worm. You know that. Also in Czech Republic, you have early birds that get a worm. Don't you? So this bird says, worm, early bird, the worm is over there. I show you. There's the bird, the worm, and the bird flies. And in Bavaria, we say it gets the Batst. I don't know the vocabulary in English, so I say the Batst. It describes a phase transition from the more solid to the more liquid under mechanical work. So that's what happens, and to understand how to detect nanoparticles, we have to understand how light behaves in matter. Let's imagine that light is a runner that runs with a constant step frequency along, for example, along the stage. And I show you this. You have a constant step frequency and you make a certain step size. The frequency makes the color of the light and it goes with speed of light, the light wave. And now you imagine you make aqua jogging. I don't know, do you know aqua jogging? Aqua jogging is a sort of, old people like to do that. They go to the swimming pool, but not for swimming, what normal people do, but they go there for running. This has several advantages. You can, you don't come far. You can watch a young and crispy swimming teacher, and you can talk to your neighbor during jogging. And as you all know, if you run underwater with the same step frequency, then you don't come as far as in the dry. The same is for light. You have the same light frequency, but because the optical medium is more dense, then the light cannot propagate as fast as before. So the frequency doesn't change. So imagine if you have a flood here, you have a huge flood, so the last row is underwater, you still see that I have red shoes, but later. That's the basic principle, and that we just have to exploit and to measure, because in the nanoparticle the light takes less space, and we have to just to measure this. Yes, here it is. That's too far. So we have to measure this with an optical resonator. Optical resonator that has two mirrors, and in between there is exactly at a distance of half a wavelength, a multiple of half a wavelength, we have a light wave. This it has really be the distance has really exactly be the distance of a light wave, and the light wave, you all know, is very short. The wavelength of light is very short and very precise. So we have to keep the length exactly at the perfect length, exactly, perfect length. And we do this electronically. This guy, he keeps the mirror distance perfectly, and as we're in public service, we don't trust him. He has to write down what he does. That's what he does. So it's a bit wiggling around. It's a bit jittering because every time the colleague walks along the floor, or other colleague in the basement, we're on the second floor, that the colleague in the basement drops his pencil, that makes slight vibrations. And now the nanoparticle comes along. It's underwater. And I tell you, never make experiments underwater. That's the worst idea you ever can have, because it will never work, or at least once. Maximum. Never worked again, it worked once. So the nanoparticle swims along, swims into this resonator. Inside the nanoparticle, the light needs less space. There's a gap. This guy says, "Öha, öha." In Bavaria, we say "öha" when we are sort of amazed. He says he has to do something. You also see the light. And what happens, he regulates. He should now regulate. It's a bit too slow. In Bavaria, we're a bit slow. He writes down this peak, and when the peak is there, the nanoparticle is there. And at least in the dream of the experimentalist, when the nanoparticle is gone, everything is like before. This experiment worked once. And that's why I can show you a video of this experiment. Here you see in red the two mirrors. In white the scattered light of the nanoparticles, and in blue the movement of the mirrors. If you now, so if it's white, it's jittering there, and the other way around. So if you now wonder that you don't see the mirrors moving, that's because the movement is very, very, very small. It's of a distance of several atom radii. That's like a nanometer or even below. To give you a comparison, let's think of a huge plane, like an Airbus. You buy an Airbus, and compared to the price of an Airbus, 1 meter, so if you compare, an Airbus costs like 1 meter, and if you compare this length to the Airbus, this is the price of an office clip to the Airbus is the length to 1 meter. So now you know how to detect individual transparent nanoparticles. Thank you very much.